Welcome to the video to accompany Chapter 12. Today we're going to be talking about magnetic vector potential and the Biot-Savart law. You'll remember that last time in Chapter 11 we introduced the concept of magnetostatics. We talked a little bit about, we saw how Ampere's law can be used to calculate the magnetic flux density that's near a very symmetric region of charge. And we saw that Ampere's law was very similar to Gauss's law. But if you think back to electrostatics, we had a number of tools. In addition to Gauss's law, we had Coulomb's law, we had the concept of electric field, we had the concept of voltage. Those were all tools in our toolkit that we could use to solve a given electrostatics problem. So far, we only have the one tool in our magnetostatics toolkit. But today we're going to add two more, magnetic vector potential and Biot-Savart. When we talk about a chapter in which the name of two physicists appears in the title, you probably would guess that I would highlight them in the historical perspective. And sure enough, here's Jean-Baptiste Biot and Félix Savart, the two scientists who discovered the Biot-Savart law in 1820. It's amazing to me how advanced things had been even in 1820. So let's just quickly review electrostatics and magnetostatics. We've actually gained a lot of ground here, and believe it or not, as of in just a minute, we will have seen everything that we need to solve all the problems that we will face in electrostatics and magnetostatics. In particular, if you remember back to Chapter 11, we saw two equations. One of them is already one of Maxwell's equations, so the divergence of B is equal to 0. So remember that means that the sources and sinks of the magnetic flux density are always 0, that there's no place where they're created. They always form continuous loops. So we see that there's no such thing as a magnetic monopole, for example. Now the second equation here, the curl of B is equal to mu sub 0 times J, that's an early version, it's an incomplete version of Ampere's law, which we will eventually see as one of Maxwell's equations, but it's not quite ready yet. We've still got one more thing that's very important to add to that. Now as it turns out, there's a thing called Helmholtz's theorem, and we're not going to prove Helmholtz's theorem, but it says that if you have the divergence of a vector field and the curl of the vector field, then you have specified everything there is to know about that vector field. So since we know the divergence of B and the curl of B, these two quantities right here can be used to calculate B for any given region that is near a current density. Now we'd also already seen an equation that relates the divergence of E, and we called that Gauss's law. So we have both of the equations for magnetic flux density, or for magnetostatics, but we only have the divergence so far for electrostatics. Well, it's kind of just an oversight on my part that at the time I didn't mention it, but the curl of the electric field is always going to be equal to 0. So the curl of E is equal to 0. We refer to that as an irrotational field. An irrotational field is one that has no rotation. And if you think about all the examples of electric field that we've seen, many times it'll be something like a starburst, where all of the fields are flowing out away from a certain point. Or maybe if you have a positive charge density and a negative charge density, they're all going to flow from one to the other in circuits like this. But we really don't see any rotation in any of the electric fields. And as a matter of fact, it can be proven that the electric field is irrotational. So that means that we do in fact have the divergence of E and the curl of E, so therefore we can calculate E for any region near charge density. Just as a quick aside, this won't be something that you'll be tested on, but any field that is irrotational is going to be conservative. And if you remember when we talked about conservative fields, we saw that if you do any closed loop around a conservative field, that you're going to find that closed loop always must equal 0. So this is Kirchhoff's voltage law. Ultimately, Kirchhoff's voltage law can be proven to be true because the electric field is irrotational. So that's just a quick review of magnetostatics and electrostatics. Just one more quick thing. Take a moment and realize that the divergence of B is equal to 0 and the curl of E is equal to 0. So we're going to often find in this class that the magnetic flux density, or the magnetic field, and the electric field are complementary of each other, that they have a reflection, they have a symmetry to each other. And in the same way, you can see here that the curl of B is some constant times a current density, and in the same way the divergence of E is some constant times the charge density. So while the current density and the charge density and the constants vary, we see that there is really a lot of similarity, a lot of complementarity in these two equations that seem to rule all of magnetostatics and electrostatics. So let's just let's talk a little bit about some new tools that we can use to calculate these magnetostatic fields. So let's in particular see the magnetic vector potential. So magnetic vector potential is going to be a vector that we're going to define to be A. So A is the magnetic vector potential. So A right there is the magnetic vector potential. And we're going to define A to be the vector that, when we take its curl, we obtain B. Remember that B is the magnetic flux density, and that's the thing that we care about the most in the world in Chapter 12, is the magnetic flux density. So if we have A, we can find B. And so then the goal becomes, can we find A? You know, at this point, when you look at equation 12.2, you might say, I don't really see how that is useful. I don't really understand how that's beneficial, but okay, I'll go with you for now, but you better get to the point here pretty quickly. Well, let's just take a minute and substitute equation 12.2 back into Ampere's law. Just let me remind you up here. Ampere's law says that the curl of B is equal to mu sub 0 times J. Well, if we have the curl of B equals mu sub 0 times J, and we know that B is equal to the curl of A, then that's really just saying that the curl of A is equal to mu sub 0 times J. Okay, so far so good. Now, I'm going to say for the first time of about 6 times in today's lesson that we're now going to rely on mathematicians, and we're going to make a jump here that is beyond the scope of this course. Because trust me, Chapter 12 could be its own entire textbook. If I proved every single thing that's in Chapter 12, it would require 100 pages. And neither one of us wants that. So I'm going to, on occasion, defer to the expertise of mathematicians. And mathematicians have proven equation 12.4, which is that the curl of a vector field is equal to the gradient of the divergence of that vector field minus the Laplacian of that vector field. Now you might remember that we briefly introduced this Laplacian operator, and it's not one of the big three. The big three are the gradient, the divergence, and the curl. But the Laplacian it's a substitute. It's a junior varsity member of the team. And Chapter 12 is where the Laplacian really gets to shine. So I wanted to remind you that you have in fact seen the Laplacian, that the Laplacian, the del squared is basically equal to the second derivative in each of the 3 directions. So it's a second derivative with respect to x, a second derivative with respect to y, and a second derivative with respect to z. So I just wanted to remind you that you have in fact seen the Laplacian. Now we're going to rely further on expert mathematicians to tell us that we can choose the value of the divergence of A, so divergence of A, to take any value that we want. So that means that this quantity right here, we can choose that to be anything that we want it to be. In the same way that if we were going to specify an elevation, we could specify that elevation relative to any place on the planet. We could specify it relative to the peak of Mount Everest, but we choose typically to specify it relative to average sea level. And in the same way, when we specify a voltage, we can specify where we want to take the reference point. And so the reference point, we typically take that to be ground, and all other voltages are measured relative to ground. In the same way, choosing the divergence of A is sort of like setting that reference point. Now we're going to do something known as selecting the Coulomb gauge. Now that's not helpful words. All I want you to know is that if you ever see that phrase, select the Coulomb gauge, what it means is that we've chosen the divergence of A to be equal to 0. So the divergence of A is equal to 0. And we're allowed to choose it to be anything. I could choose it to be 10 or 1,000 or 1 billion. I've chosen it to be 0. And because I've chosen it to be 0, if I flip back up to this equation, that means that this term right here is going to go away. And if that term goes away, then that means that the curl of A is simply equal to the negative Laplacian of A. And we know that the curl of A is equal to mu sub 0 times J. So therefore, the negative Laplacian of A is equal to mu sub 0 times J. Or we'll just flip the negative sign over to the other side. So this allows us to have a relationship between the magnetic vector potential and the current density. So we have the current density. So the current density J, we're going to use that to calculate A. And then from A, we're going to use that to calculate B. And that's the process that we're going to follow. That's the 2-step process that I mentioned at the start of the lesson. Now, this equation right here is very, very similar to Poisson's equation. And I've just referenced back to Poisson's equation from chapter 7 so that you can see that we had the Laplacian of V is equal to negative rho sub V over epsilon 0. So if you replace charge density with current density, if you replace the magnetic vector potential in for regular potential, and typically we're going to find that mu sub 0 and epsilon 0 have an inverse relationship. So if you replace 1 over epsilon 0 with mu sub 0, you end up with equation 12.6. Now, we didn't derive that equation simply by looking at Poisson's equation. We derived it from the fundamental laws of magnetostatics, but it's nice to see that we get a result that's very similar to what we had previously seen for electrostatics as well. This similarity or complementarity between the equations for electric fields and the equations for magnetic fields is going to be a theme we're going to come back to over and over and over throughout the rest of this book. So I'm going to refer to this equation 12.6 as, quote, Poisson's equation for magnetic fields. Just as we have Poisson's equation here, and we don't specify that it's Poisson's equation for electric fields, it's just Poisson's equation because it was the first one that was derived. Up here we have the Poisson's equation for magnetic fields. And so we now have an equation that we can use to go from current density to calculating the magnetic vector potential. But you may notice that this equation, 12.6, is a little bit problematic because it is a differential equation. You know, we've kind of hidden the differential nature of it in the Laplacian operator here, but remember that that's actually a sum of 3 second partial derivatives in each of the 3 dimensions. So it's actually a differential equation, which means that it's not an easy thing for us to solve. Happily, and again, I'm going to just say, beyond the scope of this course is converting equation 12.6 down to equation 12.7. Equation 12.7 is the integral form of Poisson's equation for magnetic fields. Remember that all of our other equations that we've seen had a point form and they had an integral form. Here we're going to be able to calculate the integral form of that equation. So notice now, this is, I guess you could still say it's an integral differential equation, but it's one that is much more, I can more easily handle it. I can work with it. Because whatever I find for J, I can then just take the integral, and that will give me A. Now you'll notice that there's an R prime here, and there's an R without a prime here. There's a dV prime here. We're going to need to talk a little bit about the geometry of this problem. For one thing, we've got this R, and that R is defined by equation 12.8 as the difference between x and x prime, y and y prime, z and z prime. We square each of those differences, sum them, and take the square root. Let's look a little bit at what is the geometry of a problem like this. Oh, I should mention that equation 12.7 is derived using a method called Green's functions. Now, you may have encountered Green's functions, but you probably haven't. If you go to graduate school, and if you take a course that involves heavy-duty differential equations, you will probably encounter Green's functions. And Green's functions can be used to solve a wide variety of very complicated differential equations, and they are extremely challenging. So I just want you to be aware it's one of the most important tools for advanced differential equations, and it's also very challenging. So we're going to look a little bit at the geometry of this problem. So what we have, and I'm just skipping straight to the figure here, we have a current density, and that current density J is creating a magnetic vector potential A. And those two are at different points. You know, the current density, we don't control where that is. That's given to us by the problem, and we're probably required by the problem to calculate A at a particular point as well. So we need to have vectors that point to both of those. And we're going to go ahead and use R prime, and this is a little bit small, but we're going to use R prime to represent the location of the current density J, and just regular lowercase r to represent the location of the magnetic vector potential A. Then we're going to have this additional vector R, capital R, which is pointing from the current density to the magnetic vector potential. So this is, you could think of this as the source of the magnetic field, and this is the test point. This is where we want to find what is the magnetic flux density, or we'll find first of all the magnetic vector potential, and then from that we'll find the magnetic flux density. So keep this picture in mind, and especially keeping straight r prime and r. And then if you look at this figure, it really does help. Whoops, I didn't really need to erase test point. If you look at this figure, it really does help to see that if you what you want is the magnitude of r. Well, r, which I'll put a magnitude here, but if you don't make it bold or have an arrow over it, then that assumes that it's the magnitude. Then that's going to just be the difference between the x values. So that's x minus x prime squared, plus the difference in the y values, y minus y prime squared, plus the difference in the z values, z minus z prime squared. And so what we find then is that this is in fact the exact definition of r that we had up here in equation 12.8. So we can now tackle some example problems, and from that we can calculate the magnetic vector potential. Remember, once you find the magnetic vector potential, ultimately the goal is to find the magnetic flux density, which is just going to be the curl of A. So that brings us to our first example problem, and let me just take a minute and warn you that the calculus is going to get heavy in this lesson. I don't want to make any promises, but I think today might be the peak of calculus in this class. It's not too bad. We're only 12 chapters in. We've got about 30 chapters, 35 chapters overall. So being 12 chapters in to hit the peak of calculus is not too bad. Just hold on tight, and if you don't understand one of the steps in the derivation, back up, watch the video a second time. If you still don't understand it, please come and see me. I'd be happy to talk to you about it. So we have a current I that is going along a straight wire of length A. Now you might say, where is that current coming from and where is that current going to? And I will say, don't worry about it for now. This is an imaginary problem. And so we're going to, obviously, if this is an actual current, it has to complete a loop. I understand that, and I just want you to know that I understand that. But for today, we're going to pretend that positive charges are being created down here, they're traversing vertically upward, and then they're being destroyed when they reach the top of the wire. And so I know that that's not reasonable, but it's what we're going to assume for today so that we can solve an interesting problem. And we can actually then use the result of this problem to do some very interesting things in class tomorrow. So let's just take one point along this wire. So I'm going to take a differential element along this wire, and it is going to be a distance. I'll call that z prime. Again, remember that the primes go with the element of current density, and the not primes go with the test point that we're looking at. So this is going to be dz prime, and then I need to consider what is straight line. What is the vector that's going to go from the point where there's current density to the point that we're testing? And so this is going to be r. Well, we know from the Pythagorean theorem, we have one leg of a right triangle, we have another leg of a right triangle. So we know that the magnitude of r, which I can just represent as r, that's going to be equal to the square root of rho squared plus z prime squared. So we're making some progress. I should mention that the very first thing I like to do when I'm solving a problem like this is I like to write, what is my controlling equation? I've really only got one equation here that can be used to calculate the magnetic vector potential. And so let me just take a minute here and remind myself of what that equation is and what sorts of things I'm going to need to try to solve for. Well, one good thing, I've already calculated r. So r is in the denominator of the integral. Mu sub 0 is fine, 4 pi is fine. We do need to deal with a little bit with that current density. So let's consider, what is j of r prime multiplied by dv. Now, this equation is completely general. It gives the possibility, I'm going to erase this in a second here, but it gives the possibility that you could have entire regions of current flowing, and that those regions of current, it would be like it'd be like a stream, the water flowing down a stream or down a river. And there could be little whirlpools, there can be local things that are happening, but at every point there's going to be a particular current density, and by the way, it's three-dimensional as well. So this equation is a lot more powerful than we typically need, especially in an introductory course. So what we're going to do is we're going to simplify this. We're going to simplify it to say that rather than having a volume of current densities, I'm going to have a line of just current. So I can simplify this to say that it's I times dz prime times a sub z. Notice that dz prime is pointing in is that differential element, and az is pointing in the upward direction, so that's correct for this current, and then the current I is given in the problem. So notice that what happened was we kind of took what is a current density, we multiplied it by a cross-sectional area, and that gave us a current. And then so that cross-sectional area took 2 of the 3 dimensions out of the volume, and it left us with only the 1 dimension for dz prime. Okay, so let's go back and review this equation that we've now made some improvements to. This is going to be mu sub 0 over 4 pi times the integral, and I'll put those limits on here in a second, I dz prime a sub z divided by, and what do we know is r? R is this quantity right up here. So this is going to be, and I'll write it as z prime squared plus rho squared. Okay, so we know that the limits, I'm going to go ahead and take the center of the wire to be 0, and so this is going to go from minus a over 2 up to plus a over 2. We know that I is constant, so that's gonna pop out in front here. So this is mu sub 0 I over 4 pi times the integral from minus a over 2 to plus a over 2 of dz prime divided by the square root of z prime squared, that's not z to the 12th, it's z prime squared, plus rho squared. Now if you look in the useful integrals table, I'm gonna take advantage of a little bit of space up here above. We have the integral from minus a to plus a. Notice those limits are not correct. This is a generic integral, and we're gonna have to customize it for our particular purposes. dz divided by z squared plus rho squared, and oh, that's just a square root under there. So come on, oh darn it. So there we go. So this is a square root in the denominator. If we want to take that integral, it is actually a natural log of the square root of a squared plus rho squared, and then outside the square root is a plus a, divided by the square root of a squared plus rho squared, and outside the square root is a minus a. So that's one of the equations that's in the useful integral tables, and it's definitely going to be a useful integral to us today. And if you'll notice, that's essentially the integral that we need to solve here with different limits. So I'm gonna need to be more careful about the limits here. But let's go ahead and take the next step in this problem. So a of r is going to be equal to mu sub 0 and times I over 4 pi. I'm going to go ahead and take the a sub z out front as well because it's a constant. And let me see, anything else? Nope, that's all the constants. And now I've got a natural log. And it's going to be a natural log of, in the numerator, instead of a, it's going to be a over 2, the quantity squared, plus rho squared, plus a over 2. And in the denominator, it's going to be a over 2 squared plus rho squared minus a over 2. Now we could leave things like this. We could stop here, but there's a lot of kind of junk in there. I'd like to clean that up just a little bit, get rid of those over 2's if I can. So I'm going to multiply. What's the easiest way to do this? I'm going to multiply the numerator and the denominator by 2, and I'm just going to say times 2 over 2. Okay, so that means that I need to multiply both terms by 2. So this is going to be mu sub 0 I divided by 4 pi times a sub z hat. We're almost done, by the way. Technically, we could have been done, but I'm trying to make it just a little bit better. So when the 2 is going to go into the square root, it's going to become 4. So it's going to be the square root of 4 becomes 2. So it's like we have a square root of 4 times a over 2, the quantity squared, plus 4 rho squared. Now we can't forget that the 2 also has to multiply the a over 2. So we have a over 2 times 2, and then the same exact thing is going to happen in the denominator. 4 times a over 2, the quantity squared, plus 4 rho squared minus a over 2 times 2. Now you can already see, I'm sure, that those 2's are going to cancel. That's going to help us quite a bit. And the 4 is going to cancel with the 2 squared in the denominator. So this 4 is going to cancel with that 2 squared, and that 4 is going to cancel with that 2 squared. And we end up with our final version of this equation, which is mu sub 0 I over 4 pi times a sub z times the natural log of the square root of a squared plus 4 rho squared plus a over the square root of a squared plus 4 rho squared minus a. And that is the magnetic vector potential caused by a line segment of current I, and it has to be at a point that is along the perpendicular bisector of that line. Now that's not very helpful to us right now, but we're about to do part 2 of the problem. Part 2 of the problem is, given that result, calculate the magnetic flux density B at that same point. Okay, we got it. We're going to have some heavy lifting here, but it's going to be worth it at the end. We're going to get a result that we can verify matches what was given to us by Ampere's law. So we know if you go back to equation 11.5, we had a matrix that we could use to calculate the curl of a vector in cylindrical coordinates. And I said, don't memorize that equation, and I still don't want you to memorize it, but I am going to write it down here. And so you could derive this equation using the method of diagonals that we talked about. So B is equal to the curl of A, which is equal to, here we go, 1 over rho times the partial of A sub z with respect to phi, A sub z with respect to phi, minus the partial of rho A sub phi with respect to z, and that's multiplied by A sub rho, plus the partial of A sub rho with respect to z, minus the partial of A sub z with respect to rho, and that's times, that is times A sub phi, plus 1 over rho times the partial of rho A sub phi with respect to rho, minus the partial of A sub rho with respect to phi, and that's all multiplied by A sub z hat. Now, one secret that we don't tend to tell everybody who's outside the College of Engineering is that a lot of times when we have these big nasty looking equations, a lot of these terms are going to cancel out. And so let me just flip back up here and see, what did we get for A? If you look up here, the equation that we have for A has 2 characteristics. First of all, it only has an A sub z component. And second of all, there's no phi or z dependence at any point here. There's a rho dependence, but there's no phi or z dependence. So first of all, I know that capital A sub rho and capital A sub phi are both 0. So that means that this term goes away and this term goes away, and oh gosh, both of these terms go away. So that's pretty nice. And I'm only left with the terms that represent capital A sub z. But then I've got one more benefit, and that is that capital A sub z has no dependence on phi, so this term also goes away. I'm really only left with this term right here that says, tell me about the rho dependence of the A sub z term. Let me come back up here. There is an A sub z term, and it does have a rho dependence. 5 of the 6 terms have dropped out. Now when you see how much work we have to do to get that one term, you're going to be especially happy that those 5 terms dropped out. So we see that B arrow is equal to negative partial of A sub z with respect to rho, and that's going to be in the A sub phi direction. Now let's plug in what we found in the previous example. Partial with respect to rho of mu sub 0 I divided by 4 pi times the natural log of, and the numerator is the square root of A squared plus 4 rho squared plus a, and the denominator is a squared plus 4 rho squared minus a. And I don't need to include the a sub z unit vector because we'd already specified that this has to just be the z component. So I need to take this derivative. Well, some parts of it are going to be easy and some parts of it are going to be hard, and I can make the harder parts a little bit easier. Oh, I did forget this a sub phi right here. Must not forget that. I can make the difficult parts a little bit easier by using some substitutions. So let me just quickly make an observation here, and that is that this a squared plus 4 rho squared, that looks like it's something that I'm going to want to substitute. So let's let, oh goodness, that was horrible. Let's let u, I don't know about you, but my calculus professor always used u for substitutions. Let's let u be a squared plus 4 rho squared. And I like to write this, especially if I'm going to be doing derivatives, as a squared plus 4 rho squared to the 1/2 power. That makes it easier for me to see how to apply the power rule. Now I'm going to calculate what is the partial of u with respect to rho. So I'm not worried about this big nasty equation at the top right now. I'm just focusing on this quantity right here. So how do I find the derivative of that with respect to rho? Well, I'm going to start out by doing the power law, the power rule. So I'm going to bring that 1/2 down in front times a squared plus 4 rho squared. And then the 1/2, I'm going to subtract 1 from that, and it becomes minus 1/2. And so far, so good. But now I have to do the chain rule and say what is the derivative of that inner part with respect to rho. Well, the derivative of a squared is just a constant, so that's 0. And what's the derivative of 4 rho squared? That's 4 times 2 rho. Okay, I can cancel, let's see, I'll cancel that 2 with that half. And I'm going to go ahead and re-represent the negative 1/2 as something in the denominator. So this is going to become 4 rho divided by the square root of a squared plus 4 rho squared. So I've sort of preemptively done, I've prepared to do a substitution, and I've calculated the derivative of that substitution because I know that the chain rule is going to require that before this problem is over. Okay, so now let's come around here and let's say, going back to what we just found, b is equal to negative mu sub 0 I over 4 pi. After all, those are all constants, so they can move out of the derivative, times the partial derivative with respect to rho of the natural log of what? Well, that thing, the square root of a squared plus 4 rho squared, that's just u. That's what we defined u to be, plus a. And in the denominator, the square root of a squared plus 4 rho squared, that's just u minus a. Well, that's looking a little bit better. And I'm now going to say this is equal to minus mu sub 0 I over 4 pi times the partial derivative with respect to rho of, and I'm going to take advantage of the fact that the natural log of a quotient is the difference in those natural logs. So this is the natural log of u plus a minus the natural log of u minus a. So that's just applying an identity associated with natural logs. Okay, well, you know what? I know that the derivative of a natural log is just 1 over that quantity. And so I'm going to be able to go ahead and do this derivative now. I'll do it on a new line. So b, oops, forgot my arrow there. B is equal to minus mu sub 0. Be real careful with these signs. Don't want to forget a negative sign and end up getting the whole quantity just off by 1. So when I take the partial derivative with respect to rho of the natural log of u plus a, I'm going to get 1 over u plus a. But then I need to follow the chain rule, which says do the derivative of u with respect to rho. And then I'll do the same thing for the second term. Whoops, that's not plus, that's minus. So it's minus 1 over u minus a times the partial of u with respect to rho. Now, if that step was confusing, all I did there was first of all, I broke the natural log into 2 natural logs. I applied the fact that the derivative of the natural log is 1 over that quantity, and then I had to use the chain rule by putting a du d rho at the end of each one of those terms. Well, I can now substitute some things in, because I know that this is minus mu sub 0 I over 4 pi times, and I'm going to factor the du d rho out in front, du d rho, and now I've got 1 over u plus a, so it's I'll have the u plus a down here and the 1 minus 1 over u minus a. Now what we know is that we really need a common denominator there if we're going to simplify that. So I'm going to multiply, I'm just going to cut this off a little bit here. I'm going to multiply this first term by u minus a divided by u minus a. That leaves it unchanged, so there's no foul there. Well, that just made it look horrible. So we have u minus a over u plus a times u minus a, and then I'm going to take what used to be just u minus a, and I'm going to multiply it by u plus a divided by u plus a. Okay, so another step of substitution. B is equal to minus mu sub 0 I over 4 pi. Let's go ahead and plug in what we know for partial of u with respect to rho, because remember we found it here. So I'm going to erase those circles because I was just trying to draw your attention to it. This is times 4 rho over the square root of a squared plus 4 rho squared. And then inside the bracket here, I can see that I have u minus a, and looking at the numerator, u minus a minus the quantity u minus a. So the u's are going to cancel because one is positive and the other one is negative. The a's are both negative. So I end up with minus 2a divided by, and of course the u plus a times u minus a is going to give me u squared minus a squared. It's down the home stretch here. Oh, the two minus signs, those are going to cancel out. So I don't have to worry about the minus signs anymore. This 4 can cancel with this 4. Yeah, we'll do some more in just a minute, but for now that's good. Mu sub 0 I over pi times the square root of a squared plus 4 rho squared times 2a divided by what's u squared? Well, u was defined to be this quantity right here. So u squared is just going to be a squared plus 4 rho squared. And then don't forget this minus a right here. I'm sorry, minus a squared. The a squared and the minus a squared are going to cancel. This 2 will cancel with half of this 4. And this is left with mu sub 0 I over, let's see, over 2 pi rho squared times a in the numerator, and then there's also in the denominator an a squared plus 4 rho squared. Let me just compare that with my final answer. 2 pi, oh, there's a rho somewhere. Oh, this rho right here, I forgot to bring that into the next term. So that rho right there would have canceled with 1/2 of these rows right here. So this is actually just rho, not rho squared. 2 pi rho square root of a squared plus 4 rho squared. And then I forgot this a sub phi. I forgot it for like 5 steps in a row. So I'm going to go back in and add the a sub phi. So here's an a sub phi, and here's an a sub phi. I apologize for this. A sub phi. I hated when my professors did this. A sub phi. Here's an a sub phi, and here's an a sub phi, and here's an a sub phi. Now let's just double check a couple of things. First of all, we should be able to use the right-hand rule to determine the direction that this magnetic flux density should be going. This calculation has just shown us that it's in the a sub phi direction, but let me scroll back up here and look at the picture. And if you put your thumb in the direction of the current density, and you see where are your 4 fingers going when they sort of intercept the page at the point that we're considering, well, my 4 fingers on my right hand are going into the page. And into the page, according to this little legend right here, is positive a sub phi. So it seems that not only have we correctly gotten all the unit vectors, but we've also kept the sign correct as well. I would also expect that as I increases, that the magnetic flux density would increase, and that's in fact the case. I would also expect that as rho increases, that the magnetic flux density is going to decrease. We get further away from that current density, and that in fact is the case here as well. Now let's consider, given that two-step process, now given that result, determine the magnetic flux density a distance rho away from an infinitely long wire carrying a current I. So this is just as simple as calculating the limit as A goes to infinity of that thing we just found, mu sub 0 I times A sub phi divided by 2 pi rho times the square root of A squared plus 4 rho squared. Well, I'm going to pull some things out of that, but just because there's a lot of stuff going on there. So I'm going to have mu sub 0 I times A sub phi divided by 2 pi rho. None of that is going to be impacted by taking the limit as A approaches infinity. But what will be impacted as A goes to infinity is everything else, which is going to be A divided by the square root of A squared plus 4 rho squared. Well, if A is infinitely large, then 4 rho squared is going to become irrelevant. And if 4 rho squared becomes irrelevant, then the denominator is just the square root of A squared, which is really just A. And so if that happens, then we can cancel A with the square root of A squared, and the whole limit that's there is just going to go to 1, and this leaves us with mu sub 0 I over 2 pi rho times A sub phi. And if you go back and look in chapter 11, when we had an infinite wire, so we had a lot of symmetry, so if there was an infinite wire, then we were able to calculate the magnetic flux density surrounding it, and we got, in fact, exactly the same quantity. So we've just done an awful lot of work to figure out what happens if the wire is not infinite. If the wire is not infinite, then this is the expression for the magnetic flux density. And you might say, that's not worth it. And I would say, yeah, it was a lot of work, but to be able to calculate the effect due to a finite wire, a finite, I guess you could call it line segment of charge, that may be exactly what you need to solve your problem. And in this case, we were able to solve it using magnetic flux density, using magnetic vector potential. But nonetheless, that was a lot of work, and we'd like to simplify the process if we could. So we're gonna try to take that two-step process. Remember that we had to calculate A, then we had to take the curl of A to find B. We'd like to break that into just one problem, into just one calculation, and that's going to be what the Biot-Savart law does for us. So Biot-Savart is going to combine these two steps together into just one step, and that's going to allow us to solve the problem not instantly, but in one step. So remember, we know that B is defined to be, or I'm sorry, A is defined such that B is the curl of A. And we also have an expression here. It's really our only expression for calculating A. So I'm going to plug that into that equation. And so now I know that the curl of that thing in parentheses is equal to B. Well, right away now I have an equation that allows me to go directly from J to B. It's kind of a hassle of an equation to work with, but we can make some progress on this. And now I'll just say we're going to bring the cross product into the integral, and when we do that, now we're going to have to introduce this unit vector a sub r. And if you're saying, hey, why did this r here? Why did that r become an r squared? Well, it's part of bringing in the a sub r. So I just want you to know that there are several steps of algebra, several steps of vector calculus and vector algebra that I've omitted between equations 12.9 and 12.10, but 12.10 is very close to what we want. 12.10 is actually more than what we need. 12.10 is going to give us that idea of I've got a three-dimensional flow of current that's going in complex patterns. And typically in this class, at least, we're not going to tend to see those very complex three-dimensional patterns. We're just going to be working with a single wire of charge, a single wire of current. So we can simplify equation 12.10 down to equation 12.11. Again, I'm omitting the details of that simplification, but I think that what we want to learn more about in this class is more about applying these rules rather than deriving them. So we end up with, and this is an equation that gets a box because it deserves it, the Biot-Savart law. So the Biot-Savart law is going to allow us to take information about current. In this case, it's a constant amount of current that's flowing in a direction dl. We're going to cross that with the vector that goes from that current to the point we're testing. We have this r squared, which is the distance squared from the point of the current density, or the point of the current to the point that we're testing. And we're going to take a closed loop integral of this. Now, I just want to take a minute and say, that we're not going to be really, we're not going to enforce this closed loop integral here. So this could be an open loop integral, but in reality, if we're really doing a real world problem, all circuits are closed loops. And so I'm going to leave it in here as part of the equation, but then when we do the examples, you're going to see that we don't actually close the loop most of the time. So I just want you to recognize that the Biot-Savart law is designed for a closed loop of current to flow, but sometimes we're going to tackle problems that don't really involve a closed loop. So that's all that we needed to know for deriving Biot-Savart. Now let's go ahead and apply Biot-Savart. So we can now take example 12.4. We're going to repeat the calculation of the magnetic flux density caused by the current I along a straight wire of length A, this time using Biot-Savart. So it's exactly the same problem that we saw in the previous 3 example calculations, but we're now going to solve it using a different method. So we're going to again take a little piece of the current here, and it's going to be a distance z prime above the origin, and we're going to call this dz prime. By the way, we're still going to consider the primes to be pointing to the location of the current density, and the unprimes are going to be pointing to the point that we're testing. So let's again consider what is the distance between those two. So this is going to be r is equal to the square root of, and we're going to have rho squared plus z prime squared. So we know our Biot-Savart equation, B of r, is equal to mu sub 0 over 4 pi times the integral. I'll go ahead and call it closed loop, even though it's not going to be in this problem. I dl prime crossed with a sub r, that's divided by r squared. Well, we already know what r squared is because we just found r right here. But let's go ahead and do some additional work here. We know that dl prime is going to be dz prime times a sub z. Because to get from the origin, and I'm calling this the origin, to get from the origin to the point of current density, I need to go z prime in the a sub z direction. And oh, that has an arrow above it. And then I also can calculate a sub r. A sub r is a unit vector that is pointing from the point of current density down to the point that we're testing. So a sub r is in this direction right here. Well, I know that to go the full length of that red line, I'm going to need to go rho units in the a sub rho direction. So this is rho a sub rho. And then I'm going to need to go negative z prime. So I'm starting here, and I'm going to here, so I need to go down z prime units in the a sub z direction. So I would be done, except for the fact that this is no longer a unit vector. So I need to unitize it. I need to make it into a unit vector, which means that I'm going to divide by its magnitude, which is rho squared plus z prime squared. Okay, I'm feeling really good about this. We've identified dl prime, we've identified a sub r, we know r squared. So now it's time to go ahead and plug all of this in. Let me just take a minute and observe a couple of quick facts here. We know that there are three cross products that we're going to need to work with. We know that a sub rho crossed with a sub phi is equal to a sub z, which you can get from this legend right here, or if you go back and look in chapter 2, these are all written down there. A sub phi crossed with a sub z is equal to a sub rho, and a sub z crossed with a sub rho is equal to a sub phi. And so all three of those can again be derived from the legend. Now you might say, why do you need to know that? Well, the next step is going to make that clear. So B of r is equal to, okay, we got mu sub 0 I over 4 pi, and we're going to do an integral. It's going to be an integral from minus a over 2 to plus a over 2, and the numerator is going to be I times dl. Oh, I already brought the I out, so it's just dl. So this is dz prime a sub z. So I took that from right here, and that's going to be crossed with a sub r. And a sub r is this quantity right here. Well, I'm going to go ahead and do the numerator of that. So this is rho a sub rho minus z prime a sub z. and then I'm going to have the rest of this, so the denominator of that is going to be down here, rho squared plus z prime squared. And then must not forget this r squared that's in the denominator. So r squared is just going to be rho squared plus z prime squared. So it was the square root. When we squared it, the square root went away. So I can do one more step of simplification here before I do the integral, and that is that this denominator has rho squared plus z prime squared to the first power, and rho squared plus z prime squared to the 1/2 power. The square root is a 1/2 power. So this denominator is going to become rho squared plus z prime squared to the 3/2 power. So it's mu sub 0 I divided by 4 pi, the integral from minus a over 2 to plus a over 2. We'll do the numerator here in just a second. So this is rho squared plus z prime squared to the 3/2 power. Now what's the numerator? Now we've got a sub z crossed with a sub rho. Well, if I come up here and see a sub z crossed with a sub rho, that gives me a sub phi. So I'm going to bring in the dz prime times rho. So that was the dz prime from here and the rho from here, and then a phi. Then you would say, well, what is az prime? What is az hat crossed with az hat? Well, anything crossed with itself is equal to 0. So it turns out that that second term is just going to go away. So this equation that we've written here is actually complete. We need to do the integral, but we are now ready to do the integral. We can pull this a sub phi hat out in front, and let me just also give you a quick reference here to an integral on the useful integral table. This is dz divided by, and we've actually already used this one, r squared plus z squared to the 3/2 power is equal to, not 1, it's equal to z divided by r squared times the square root of r squared plus z squared. So that's the integral that we're going to need to be solving. We can pull the rho out in front of the integral. We can pull the a sub phi out in front of the integral. And so we get the penultimate version here is going to be b of r is equal to mu sub 0 I over 4 pi times rho times a sub phi. And then now this is the integral of dz prime over rho squared plus z prime squared to the 3/2 power. It's going to be exactly this integral right here. So this is going to become z prime divided by rho squared times the square root of rho squared plus z prime squared. And this is evaluated between, and I should clarify that this is z prime equals minus a over 2 up to z prime equals plus a over 2. So all that really remains now is for us to plug those two limits of integration into our problem. So we have mu sub 0 I times rho times a sub phi divided by 4 pi. And I'm going to plug in z prime equals a over 2. So this is a over 2 divided by rho squared times the square root of rho squared plus a over 2 squared. And then subtract the lower limit. So that lower limit is minus a over 2 in the numerator divided by rho squared times the square root of rho squared plus negative a over 2, the quantity squared. Well, I'm going to simplify that a little bit. Mu sub 0 I rho times a sub phi over 4 pi. I have a over 2 in the numerator of the first term minus negative a over 2 in the numerator of the second term, and the denominators are going to be identical because this negative sign gets squared. So this simply becomes a over rho squared times the square root of rho squared plus a over 2, the quantity squared. And just as we did last time, I'm going to multiply this by 2 over 2. So this becomes b of r is equal to, now let's see, this, I don't want that 2 there. I want that to cancel with half of that 4. So this becomes mu sub 0 I. And this rho squared, half of that is going to cancel with that rho right there. Mu sub 0 I times a sub phi divided by 2 pi. And then, and now I've got this 2 right here is when it comes into the square root becomes a 4. So this, oh, I don't know why that disappeared. That becomes a 4. And so this becomes 1 over the square root of 4 rho squared plus, and that 4 cancels with the 2 squared in the denominator of that second term, so this just becomes a squared. And so if I can write that out a little bit nicer, this is going to be mu sub 0 I times a divided by the square root of a squared plus 4 rho squared times a sub phi, and that is my final answer. And if you just remember, mu sub 0 I times a over the square root of a squared plus 4 rho squared, that's exactly what we got when we did the two-step method. So we had mu sub 0 I, this equation right here, mu sub 0 I times a divided by 2 pi rho times the square root of a squared plus 4 rho squared, and then an a sub phi on the end there. So we got exactly the same result in a slightly simpler, you might say, is it a lot simpler? Well, I think it is considerably simpler. We only have one step, and none of these steps were incredibly hard. You know, we figured out what is dl prime, what is a sub r, what is r, plugged all those things in, did some cross products, looked the integral up in a table, or heck, plug it into Wolfram Alpha or Maple or whatever it is that you like to use, assign the limits of integration, do a little bit of simplification, and we come up with the final answer. Let's do another calculation here. This one, using the Biot-Savart law, we're going to calculate what is the magnetic flux density at a point Z above a loop of current. Okay, so we're going to start with our Biot-Savart law. B of R is equal to mu sub 0 over 4 pi. This one will, in fact, be a closed loop integral of I dl prime crossed with a sub r divided by r squared. Now let's again do some simplifications. I know that dl prime in this case is going to need to be moving along the distance of the loop right here. So dl prime is going to be a times d phi prime, and that's now going to be in the a sub phi direction. So it's in the a sub phi direction. So this is a times d phi times a sub phi hat. So that's going to be the dl. And we can calculate r. Well, r is going to be the vector that points from the point of current density up to the test point. Oh, that's horrible. Let's do that better. Pointing, I can do it better like this, but remember the arrow is pointing from the current density up to the test point. So that's r. So I know that r is equal to go from the current density to the test point, I need to go minus a in the a sub rho direction plus z in the a sub z direction. And so the magnitude of r is just going to be a squared plus z squared, take the square root. And then the unit vector a sub r is going to be equal to minus a times a sub rho plus z times a sub z divided by the square root of a squared plus z squared. Okay, so we've actually done all of the preliminary steps that we need to do. So let's go ahead and plug all of this in. We know that b of z, so now it's a function of the distance z above the center of the loop, is equal to mu sub 0 I divided by 4 pi times the integral of, it was I times dl, the I is already out in front, so it's just the dl, so that's going to be a times d phi prime times a sub phi, and that's going to be crossed with negative a times a sub rho plus z times a sub z. And in the denominator, we're going to pick up the r squared, which is just going to be a squared plus z squared. But then we also have to grab this square root that was in the denominator of the unit vector, so it's times the square root of a squared plus c squared. And hopefully you can see why I wanted to do a second example, because when we do this second example, it really shows the pattern of solving these problems and how they're often quite similar to each other. So we need to know what is a sub phi crossed with a sub rho. And a sub phi crossed with a sub rho gives me negative a sub z. So a sub phi crossed with a sub rho equals negative a sub z. Remember that if you do the cross product in the opposite order, you get a negative sign. So this is equal to mu sub 0 I over 4 pi times, and the integration limits are well, we're not ready for the integration limits yet. So this is still just an integral of, now there'll be an a times d phi prime times a negative a times, and now I end up with the negative a sub z. Now remember that the a is actually the radius of that loop, and a sub z is actually a unit vector that is pointing in this direction. So this is a sub z. Then we're going to end up with another expression, which is going to be a sub phi crossed with a sub z. Well, a sub phi crossed with a sub z is going to give me positive a sub rho. So this is plus a times z times d phi prime times a sub rho, and this is all divided by a squared plus z squared to the 3/2 power. Now it turns out that these negative signs are going to cancel. I'll be able to combine the two a's into an a squared. The integration now is with respect to d phi, so I can see that that's from 0 up to 2 pi. I need to go around the full loop. Interestingly, there's going to be a part of this magnetic flux density that is pointing in the upward direction. So that's going to be part of it. But then there's also part of it that's going to be pointing in this direction as well. Well, this component right here is going to be perfectly canceled by a component that's in the opposite direction. Remember that in some cases, we've taken a point along the charge or the current. We've taken an opposite point along the charge or the current. And we found that when we do that, that the horizontal components cancel each other out. And that's what's going to happen here as well. We could do a lot more work to prove that this term is going to go to 0. When you do the integral of that term, it all goes to 0. So I won't do that extra work. I'll just tell you that in fact that this cancels because opposite points, which means points that are 180 degrees out of phase with each other, opposite points have opposite signs. So the point that is caused by this one is going to be canceled by this point right here. So this becomes mu sub 0 I over 4 pi times, the negative signs canceled, so I had a squared times a sub z. Those are all constants. As a matter of fact, a squared plus z squared to the 3/2 power is also all constants, because the variable of integration is only phi. So this really it's phi prime. So it really just becomes that. So this integral is as simple as it can be. Mu sub 0 I over 4 pi times a squared a sub z divided by the a squared plus z squared to the 3/2 power times 2 pi. So that integral just results in 2 pi. The pi's are going to cancel. The 2 is going to cancel with half of the 4. I think that's everything that can cancel. So this is going to leave behind mu sub 0 I times a squared divided by, there's a 2 times a squared plus z squared to the 3/2 power, and it's in the a sub z direction. Let's check a few things that we can verify. You know what, I would expect that as the current increases that the magnetic flux density would increase, and sure enough it does. I'd also kind of expect that as the surface area of the loop increases, as a squared increases, I think I would expect that the flux density would also increase, and there is an a squared in the numerator. Let me just think about this for a second. Actually, maybe I think that it would decrease because the points of current are going to be moving further and further away from the test point. So yeah, there's an a squared in the numerator. There's kind of an a cubed in the denominator. We'd have to neglect the z squared, but that would give us an a cubed in the denominator. I would also expect that it would be in the a sub z direction, because if you put your hand in the direction of the current density, and this is one of those things I can't show you in this video, put your thumb in the direction of the current density, then we would expect that all of the elements of this loop would all be causing the current, would all be causing the magnetic flux density to be pointing upward. So you put your thumb in the direction there, and when we curl our fingers, the other four fingers go up there. And so that's a horrible drawing, but you get the idea that each one of these points along this loop is going to be contributing an a sub z component to the magnetic flux density. Last thing for today, and it's very brief, we've really covered the main material. Just wanted to mention that there is a thing called magnetic dipole moment. Now, a moment is a thing that you do some pre-calculation to calculate this quantity that can be useful to make other calculations simpler. Mechanical engineers do it all the time with moment of inertia. Civil engineers have moment of inertia. They have other types of moments, and we don't really tend to use moments very much. But here's one place where we do, and that is that we're going to do some pre-calculations on a loop of current. And so you can see here I have a loop of current which has an amount of current I flowing through it, and it has a radius of A. I'm going to go ahead and I'm going to take the surface area of this loop, and I'm going to multiply it by the amount of current that's flowing around that loop. So this is pi a squared, that's the surface area of the loop, multiply it by I. This a sub z, it's z in this case. If the loop were rotated in a different direction, that a sub z would be pointing in a different direction. If we do this calculation of a magnetic dipole moment, so this is a magnetic dipole moment, and that should either be bolded or it should have an arrow over it. The magnetic dipole moment M is I times pi a squared times a sub z. And so let's just quickly say what is going to be the magnetic dipole moment of a loop of wire in the xy plane, and we'll assume that the current is flowing counterclockwise when viewed from above. A radius of 2.5 centimeters with a current of 100 milliamps. Well, M is going to be I times pi a squared times a sub z, and I is 0.1 amps multiplied by pi times A. A is 0.025 meters. Yep, that's correct, squared. And when I plug that into my calculator, I get 196 times 10 to the minus 6th amp meter squared, which I will represent as 196 microamp meter squared. The units on moments are often weird, and they often don't represent anything that's a physical representation. Just know that we do the calculations of a moment so as to be able to make our lives easier in the rest of the problem. And as an example of this, let me flip back up to the result that we just found earlier. This result right here, you'll notice that if we were to calculate if we were to calculate this quantity, then we could then plug in what we know about the magnetic dipole moment, and we could also plug in what we know about the R is the square root of a squared plus z squared, and it would simplify that equation substantially. So this M right here, remember that this is going to be equal to I times pi a squared, and in this case in the a sub z direction. This R, this is going to be really a squared plus z squared to the 3/2 power. The 2 pi right here is basically canceling part of the pi right here, and then the mu sub 0 is along for the ride. But if we do all of these substitutions, we end up with a substantially simpler version of the equation, and that's going to make our lives a lot easier when we're solving for the bigger problems that are going to involve more loops. So, summary for today, we saw that we have 4 equations, 2 that control all of electrostatics and 2 that control all of magnetostatics, and that is a sufficient and complete set of equations to do all of the problems that we've faced so far. But there are lots of ways that we can do things a little bit more easily. One of them is with magnetic vector potential. where we've defined the magnetic vector potential such that if you take its curl, you get the magnetic flux density. We, quote, chose the Coulomb gauge, which meant that we take our 1 degree of freedom. There were an infinite number of vector fields that would obey this first equation, but there's only one that obeys both of these equations. And so we're choosing that one. We're choosing the Coulomb gauge, which means that we've identified that the divergence of A is equal to 0. We can, from that, get Poisson's equation for magnetic fields. That's my name for it. I don't know that other people tend to call it that. We end up with this expression, which we can have in point form and in integral form. We can do a little bit more work and take those 2 steps, combine them into 1 step, call that the Biot-Savart law. And the Biot-Savart law can then be used to solve any arbitrary problem of currents flowing in an arbitrary shape surrounding a particular point. And in particular, we saw 2 examples. We saw a calculation at a distance rho from a wire of length A, had to be along the perpendicular bisector, and at a distance z above the center of a loop of radius A. We saw these 2 equations. And so if you're solving problems that involve, maybe you could do a piecewise calculation. If you knew that you've got, say, several currents, maybe you have a square of current like this, well, you could break that into 4 problems, and each one of those 4 would be able to apply this result right here, for example. And if you had a circular, maybe you had a series of circles that could form a disk, you could perhaps get an equation that would come from this one right here. And then finally, we talked about the magnetic dipole moment, which is I times pi a squared, where this is the surface area, I times A sub z.